In our last video, we talked about different quality of service mechanisms, and we said that one of the first things we wanted to do was to classify traffic. We wanted to recognize traffic as being a certain type of traffic, and then we want to mark that traffic. And by marking traffic early on in its travel, that saves us from having to do extensive reclassification later on. The next route or the next switch, it can very quickly, very efficiently look at that marking and make a decision, like a forwarding decision or a dropping decision based on that marking. And in this video, we're going to talk about those markings. We could have markings at layer 2. We could have markings at layer 3. First, let's consider our layer 2 markings. This is a class of service marking that we have here at layer 2, or a CoS marking. Some people pronounce that a cause marking, a CoS. And this is a 3-bit value. And if we've got 3 bits at our disposal, ask yourself, how many possible CoS values could we have? Well, that's going to be 2 raised to the 3rd power, 2 because we have 2 possible binary values, 0 and 1, and the 3rd power because we have 3 bits. That's going to give us 8 possible combinations, meaning that a CoS value could take on any value in the range of 0 through 7. However, Cisco says, do not use 6 or 7. Those are reserved for network use. So if we're setting something up where we want to mark our production traffic, we should not go higher than a CoS value of a 5. Interestingly, a Cisco IP phone, it automatically marks voice packets with a CoS value of a 5. It does that for us. Now, these CoS values, what bits exactly are they altering? Well, normally when we think of a CoS value, we think of a frame as it flows over a trunk. We could do this over a .1Q trunk. We could do this over an ISL trunk. Now, in modern networks, we typically are going to be using .1Q trunks. But for completion's sake, I wanted to show you how we do it with an ISL trunk as well. With an 802.1Q trunk, we have 4 bytes that get added to our frame if we're tagging that frame. We've got 4 bytes, got tag bytes and tag control bytes, and in those 4 bytes, we've got 3 bits in a field called the priority field. And it's those 3 bits we use to set our CoS value. If we have an ISL trunk, then there's a VLAN field, and in that VLAN field, we use 3 bits to give us our CoS bits. So over a trunk, ISL, or .1Q, we have these 3 bits. However, it is possible to mark a layer 2 marking even coming out of a PC that doesn't have a trunk connection, just coming out of a network interface card. Now, I know there are some network interface cards that can actually do a trunk, but I'm not talking about those. I'm talking about a typical network interface card. If that network interface card supports something called 802.1P, where the P is for priority. What this does is, it looks a lot like a .1Q trunk, honestly. If we look at one of those frames, it adds on those 4 bytes, like a .1Q trunk does. And the reason it adds on those 4 bytes is it wants to have this priority field so that we could have those 3 CoS bits. But here's the difference. The VLAN ID contained in a .1P marking is all zeros. We're not saying it belongs to any VLAN. We're leaving that set to all zeros. But if your Cisco Catalyst switch is configured for it and your PC supports it, the network interface card in your PC, sure, you can mark layer 2 markings coming out of your PC going into your Cisco Catalyst switch. However, there is a challenge. Think about what happens to layer 2 information when it tries to cross a router boundary. Think about MAC addresses, for example. What happens on an Ethernet network as an Ethernet frame travels through a router? The source and destination MAC addresses get rewritten, don't they? The same thing happens with our CoS values. Those values get rewritten to zeros. That's right, we've gone to all this trouble, all this effort to set up appropriate CoS values, and then as soon as we cross through a router boundary, they're back to 0 again. So what do? Well, the good news is we can have layer 3 markings which do survive a router hop. In fact, many of our Cisco Catalyst switches, as soon as we enable quality of service, they will automatically sort of play an if-then game. They'll say, if your CoS value is this at layer 2, then we're automatically going to set your layer 3 priority marking to some value. And let's talk about those different layer 3 markings that we might have. Our layer 3 markings are going to be on our IP header. And with IP version 4, there's a byte in the header that's called the TOS byte, the type of service byte. There's a similar byte in an IP version 6 packets header called the traffic class byte. And a byte, of course, has 8 bits. And we're going to be able to use some bits in that byte to set a priority value. Now, for years, a really common way of setting a layer 3 priority marking was to use the 3 leftmost bits in that toss byte. And using those 3 leftmost bits, it's a lot like QoS. We've got 8 possible combinations. And that value is called an IP precedence value, 0 through 7, just like QoS. Also, just like QoS, Cisco says we should not use 6 or 7. Those are reserved for network use. That left us with only 6 usable values, 0 through 5. And in some network designs, we want to be more granular than that. We want to have more levels of priority than just 6 levels. So what do? Well, the good news is we can use something besides IP precedence. Instead of using the 3 leftmost bits, we can use the 6 leftmost bits. And that's going to give us a DSCP value. DSCP stands for Differentiated Services Code Point. And by using 6 bits instead of 3 bits, how many values does that give us? Well, let's say 2 raised to the power of 6 is 64. We're going to have values in the range of 0 through 63. 64 different values for DSCP. However, that's almost too many. Think about this. Let's say on my network that I declare that a value of 26 is awesome. That's my favorite traffic type. But on your network, you might say, 26, that's like dirt on my network. There's not a relative level of priority. That's the issue. The good news is the IETF standards body came along and they pre-selected 21 of those 64 values. And instead of having to remember a bunch of numbers, they gave them names. These names are called PHBs, per hop behaviors. And these 21 values have relative levels of priority. So if you and I both agree to use one of these pre-selected per hop behaviors or a collection of per hop behaviors, then suddenly we do have relative levels of priority where we can have traffic traveling between our networks without getting confused about what's high priority and what's low priority. In fact, let's take a look at those 21 different values. Now, each of those 21 values fall under one of 4 different categories. Here are those categories. We've got default, EF for expedited forwarding. We have class selector, and we have assured forwarding. Now let's talk about each of these. Beginning with default. A default per hop behavior has a decimal value of 0. So if we look at the 6 bits making up the DSCP value, it's going to be all zeros. It's going to be 0, 0, 0, 0, 0, 0. Now, EF is what we should typically assign to our highest priority traffic, like our voice over IP traffic that's latency sensitive. In fact, good news, our Cisco IP phones, not only do they mark a COS value of 5 at layer 2, they also mark a layer 3 DSCP value of EF for those voice packets coming out of the phone. And the decimal equivalent of EF is 46. And when you're configuring your router or your switch, you can enter either the name of EF or you can enter the number of 46. Now, it's really interesting the way the binary breaks down here. The 46 in binary looks like this. It looks like 101, 110. Remember that IP precedence only took a look at the 3 leftmost bits in the toss byte? So here's a question for you. What if this packet were intercepted by a router that only spoke IP precedence? We sent it a DSCP marking, but it only speaks IP precedence. Well, it would look at the 3 leftmost bits in isolation. If we looked at 101 in isolation, just those 3 bits, what's the decimal equivalent? 5. It's a 5. And we said that we did not want to have a value greater than 5 for any of our production traffic when it came to IP precedence. So the IETF was very strategic in the way that they selected these values. Oh, and also, please keep in mind that the last digit is always 0 for any of the IETF selected values. All 21 of those values, they're going to end in a 0 if you look at the binary. Now, class selector is designed to work in an environment where you might have IP precedent speaking routers because it is bit for bit backwards compatible with IP precedence. For example, let's say I had an IP precedence value of a 3. Even though I'm marking this with an IP precedence value of a 3, what would that look like in binary if I looked at the 6 leftmost bits? Well, IP precedence only marks the 3 leftmost bits, and a 3 would look like 0, 1, 1, but if I looked at the next 3 bits, they would be all zeros, wouldn't they? Well, this value is class selector 3. We say class selector 3 because the 3 is the IP precedence equivalent value. We say if we look at just these bits in isolation, that's a 3. What is the decimal equivalent of this? Let's figure it out. Let's put a 1 and a 2 and a 4 and an 8 and a 16 and a 32, and let's add up all the columns that have a 1 under them. So we've got a 16 plus an 8, that's 24. That's it. So class selector 3 written as CS3, that equals a decimal value of 24. And there are 7 of these class selector values. There is CS1 all the way through CS7. Now there's not a CS0 because that would be the same as default. Now there are 12 assured forwarding values. In fact, let me show you another graphic that breaks down those 12 values. Here we see those 12 different assured forwarding per hop behaviors. We're going to assign a default per hop behavior to our best effort traffic. We're going to assign an expedited forwarding per hop behavior to things like voice, things with really high priority, very low latency needs. But for the remainder of our traffic types, maybe video, maybe different types of data, we're going to assign probably a class selector value or an assured forwarding value. And notice that the assured forwarding values that we see here are written like this. We have AF for assured forwarding, and then we have a couple of numbers like 2, 1 as an example. That's the way we write an assured forwarding value. Now let's take a look at this first number, the 2. The 2 tells us the class of this assured forwarding value. Notice that we have 4 classes, 1, 2, 3, 4. What does the class mean? The class is the IP precedence equivalent value. In other words, if a packet with a value of AF21 went into a router that only understood IP precedence, that router would see this packet as having an IP precedence of 2. The first digit is the IP precedence equivalent value. So what's the next digit? The 1 or the 2 or the 3? Well, that is the drop probability. In fact, I'm going to explain even further later on in this video, but when there is congestion occurring in our queue, if we have weighted random early detection enabled, WRED, we talked about that just a bit in the prior video. If weighted random early detection is enabled, then to prevent that queue from filling up, from filling to capacity, we're going to start throwing away some of our packets. And the higher the drop probability, the more likely a packet is to be thrown away. We're going to start throwing away things in this column, high drop probability, before we start throwing away things in this column with a medium drop probability, and we're going to throw away packets with those markings before we ever start throwing away packets marked with a low drop probability. And as the queue depth, as the number of packets in that queue increases, the probability of discard begins to increase. And I'll show you a graph of that just in a few minutes. But this is not intuitive. Check this out. I'm going to just randomly pick some applications and assign them to different per hop behaviors. Let's say that an AF11, I'm going to mark my telnet traffic with AF11. Maybe AF31, I'm going to mark my video with that. Maybe AF23, let's see what I'm going to mark with that. Maybe that's going to be my e-commerce traffic. Now, here's the question. If our queue is starting to fill up, if it's getting congested, who gets thrown away first? Is it going to be video? Is it going to be our e-commerce traffic? Is it going to be our telnet traffic? Actually, it's going to be our e-commerce traffic. Not because this number of AF23, not because that number is greater than AF31. It's not. 22 is less than 26. But it's in this column. It's in this high drop probability column. And that means that it is going to be discarded earlier than any of the numbers in the medium drop probability column, and that's going to be discarded before any of the numbers in the low drop probability. I know that's not intuitive, but here's the way it works. I could have my super important traffic here with AF43, but it's going to be discarded before my lowly telnet traffic over here, simply because it's in that column. Now, let's see how the binary works. AF21. If I say AF21, the 2 we said is the IP precedence equivalent value, so let's write that out. Those are 3 bits. A 2 represented in 3 bits is going to be 0, 1, 0. The next 2 bits dictate this value. If it's a 1, it's low drop probability. If it's a 2, it's medium drop probability. If it's a 3, it's high drop probability. Now, with 2 bits, we can represent a 1 as 0, 1. And we said for all of these IETF-defined per hop behaviors, the 6th bit is always going to be a 0. So we'll put a 0 right there. That's AF21 in binary. What is it in decimal? I don't know. Let's see. Let's add our column headings. 1, 2, 4, 8, 16, 32. Let's add up the columns that have a 1 under them. We've got a 16 plus a 2. This is 18. So we could say that AF21 is 18, and our router, our switch, it will take either the number or the name. In fact, you see right here, this is the decimal equivalent for AF21. Now, I want to make sure that you know how to do this conversion, so let me give you a couple of exercises. I want to make sure that you know how to convert between a per hop behavior name and its decimal equivalent. Let's take a look at a couple of examples. I'll just make these up off the top of my head. Let's say I have an AF41. That's the per hop behavior. My challenge to you is to tell me what is the decimal equivalent of that. And you might want to pause the video and work through the math, and then we'll come back and do it together. All right, did you come up with an answer? Let's go through it together. Remember, the 3 leftmost bits make up a 4. If we represent a 4 with 3 binary bits, that's going to look like 1, 0, 0. The next digit is going to be represented by 2 binary bits, and a 1 is represented by a 0, 1. And then we said the 6th bit in all of these IETF selected per hop behaviors, it's going to be a 0. So there it is in binary. Now, what is that in decimal? Let's make our column headings. 1, 2, 4, 8, 16, 32. Let's add it up. 32 plus 2, 34. Let's see if we can go in the opposite direction. What if I said you've got a DSCP value of a 40? Could you tell me what the per hop behavior name is that corresponds to 40? If there is a per hop behavior name that corresponds to 40, remember, there are only 21 values out of those 64 that have names. You might want to pause the video and see if you can figure out the corresponding per hop behavior name for 40. Okay, let's walk through this together. Let's represent 40 in binary using 6 bits. Let's make our column headings. We've got a 32 and a 16 and an 8 and a 4 and a 2 and a 1. I'm going to have a 1 here under 32, and then I'm going to have a 0 under 16, a 1 under 8. Everything else is going to be a 0. Let's see if this adds up. 32 plus 8, yep, that's 40. So this is 40 in binary. Now, what sort of per hop behavior is this? Well, I'm noticing that the 3 rightmost bits here are all zeros. This looks exactly like an IP precedence value, doesn't it? Remember the per hop behavior that was bit for bit perfectly backwards compatible with IP precedence? Yeah, it was class selector. I think we're looking at a class selector value. So the question is, which one? Well, the class selector value is going to have a name that comes from the IP precedence equivalent value, which is the 3 leftmost bits. What is 101 in binary? If we look at those 3 bits in isolation, what is that in decimal? Well, it's a 4 plus a 1, it's a 5. I think we are looking at a CS5 value. And now that we've gone through a bit of the math, I want to take just a few moments at the end of this video and explain what I was talking about specifically when I said that we had low, medium, and high drop probabilities with different assured forwarding per hop behaviors. We mentioned earlier that an output interface can have a chunk of memory that it uses to store up packets that it's not able to send at the moment. There's not enough bandwidth. Well, I can just put those packets temporarily, hopefully very temporarily, in this buffer or a queue. However, it's of a finite size. It can only hold so many packets, and we have some really ugly side effects when we fill to capacity and we start to overflow our queue. We talked about this in the prior video. Remember my analogy with Spock from Star Trek II: The Wrath of Khan? Well, here's what we can do to prevent that queue from ever filling to capacity. We call this congestion avoidance. What we can do is use something called WRED, Random Early Detection. Well, specifically, we're going to use in the Cisco world weighted random early detection. But to understand weighted random early detection, let's first talk about the industry standard random early detection, or WRED. This is our output queue. It's only going to hold so many packets. And let's just make up a number. Let's say it'll hold 64 packets in the queue. What we can do is set some thresholds. We can say that the minimum threshold might be 20 packets. And the maximum threshold might be 38 packets, just making those numbers up. What this WRED is going to do is say, I'm not going to discard any traffic until I exceed this minimum threshold. But once my queue depth gets beyond this 20, then I'm going to introduce the possibility that occasionally, randomly, I'm going to throw away some traffic. And the probability of discard is going to get greater and greater and greater until I hit this maximum threshold. After that, I'm definitely going to be throwing traffic away. I'm not going to allow it to go over the maximum threshold. So anybody over the maximum threshold, they get discarded. Now, what Cisco did is they enhanced this concept of random early detection by looking at the marking of our packets. Those class selector markings, those assured forwarding markings, EF, default, all those markings in Cisco iOS have default WRED profiles. That's right. They each have their own minimum threshold. They each have their own maximum threshold. They each have a parameter that's going to influence the probability of discard. In fact, that's why we had those 3 columns when we looked at those 12 assured forwarding values. We had the low, the medium, the high drop probability. Let me show you exactly what that meant. We can visualize weighted random early detection like this. Here on the y-axis is our probability of discard. The higher we go, the more likely we are to throw away a packet. Along the x-axis, we have the average queue depth. How deep is the queue getting? And let's say that we have a minimum threshold of 25 packets for our high drop probability traffic. Let's say that we have a minimum threshold of 30 packets for our medium drop probability traffic and a minimum threshold of 35 for our low drop probability traffic. Now, what's going to be high drop probability? It's going to be AF 1-3, 2-3, 3-3, 4-3. Everything that ends in a 3 is going to have that same high drop probability. What's going to have the medium drop probability? Anything that ends in a 2, AF12, 22, 32, 42. Low drop probability, that's going to be AF11, 21, 31, 41. And notice that the probability of discard is increasing as the queue depth gets deeper and deeper. And once we cross this maximum threshold, at which point the drop probability is 25% in our example, once we exceed that maximum threshold, suddenly we go up to a 100% probability of discard. We're definitely going to throw traffic away if it exceeds that maximum threshold. However, just to wrap up this discussion, I want to let you know about a way that we can hopefully prevent this aggressive discarding of traffic. Remember that we've got a toss byte, we've got 8 bits, and we're only using 6 of those bits to mark our DSCP marking. What if we did something else with those other 2 bits? Well, we can do that. It's called explicit congestion notification. Here's what we can do with those last 2 bits in the toss byte, bits 7 and 8. We're using the first 6 bits for DSCP markings. What we can do with 7 and 8 is to inform the other side, to inform the other device that we're communicating with that I'm getting a little congested and I'd really rather not throw your traffic away, but I will if you don't slow down. So what ECN, what explicit congestion notification does, it's going to use these last 2 bits to say to the other side, would you please slow down? Would you please voluntarily go slower so I don't have to discard packets coming from you? Here's the way it works. Both ends of this link need to be enabled for explicit congestion notification. If they're not enabled, then these last 2 bits in the toss byte, they're going to be set to zeros. The router's not going to be capable of doing ECN, or it's not configured to do ECN if those bits are zeros. If they're either set to 0, 1 or 1, 0, you can think of those synonymously. That means, yes, I speak ECN, I'm capable of doing ECN, but I'm not currently experiencing congestion. No need to slow down. Now, if I do want the other side to slow down, what I can do is set those last 2 bits in my toss byte to 1, 1. And by doing that, I'm asking them to voluntarily slow down, to transmit to me less aggressively so my queue doesn't fill up and I don't have to start throwing things away. That's a way that we could hopefully prevent weighted RED from discarding packets that it would otherwise discard. All right, that is a very extensive look at a really important quality of service concept. Just to sum up, we said that we could do marking both at layer 2 and at layer 3. At layer 2, we had a class of service marking. We could mark on a .1Q trunk, we could mark on an ISL trunk, or if our network interface card and our switch were configured for it, we could do .1P marking. We could set a layer 2 marking without even going over a trunk. We talked about 2 different types of layer 3 markings: IP precedence markings and DSCP markings. We said because of the granularity we get, we prefer DSCP markings, and there are so many markings, we typically don't use the numbers in the range of 0 through 63. We use one of the 21 per hop behavior values that the IETF standards body was kind enough to select for us, and we went through some binary exercises seeing exactly what those numbers meant. And finally, we talked about how we were giving different levels of drop probability to different markings.